We are from Group 19 and today we'll be sharing with you on the framework of line of sight and non-line of sight classification. Satellite-based GPS loses its reliability the moment you step indoors. Walls and structures attenuate the signal, leaving accuracy at several meters at best. UWB promises centimeter-level precision as a solution, but it has its own Achilles heel non-line of sight condition, where obstacles block the direct path between devices, bridging error creeping in, undermining the very precision UWB is built on. UWB works by sending ultra-short pulses and measuring their time of flight. In a real environment, signals bounce off walls and partitions, creating multiple paths, but UWB is smart enough to identify the first direct path and use that alone to calculate distance. That's how it achieves centimeter-level accuracy even indoors.
Now let's dive into our hybrid feature fusion strategy. The goal here was to create a robust representation of our signal data by combining raw metadata with engineered statistical feature. We have categorized our final feature set into 4 categories, totaling 29 features. Firstly, we have 6 raw non-CIR features. These are standard metadata from the hardware such as first path index. Next, we have 15 PCA components derived from the raw CIR data. 5 CIR engineered features were also included. Unlike PCA components, these are human interpretable statistical measures like CIR energy and higher order moments such as skewness to capture the shape of the impulse response. Finally, we included 3 power features which help the model understand signal attenuation and path loss. A major challenge in processing CIR data is the sheer volume of samples. A full CIR approach would mean dealing with 1016 samples per signal. As you can see in the graph on the right, to capture 85% of the variance in that full signal, we will need 595 PCA components. This is computationally expensive and introduces significant redundancy. To solve this, we implemented adaptive windowed PCA shown in the left graph. By focusing on the 80 sample window centered around the first path, we significantly densify the information. In the window approach, we reached our 85% cumulative explained variance threshold using only 15 components.
We perform feature ranking using random forest classifier as seen on the left. The engineered features are ranked based on their importance. On the right, we plotted how many features we require to cover up to 80% and 95% of total importance. The features are ranked by importance. From the plot, it takes 3 features to cover 80% total importance and 5 features to cover 95% total importance. Next, we also perform a feature ranking with random forest classifier as well on our non-CIR and power features. Features at a 0% importance are removed before being fed into the model. These are considered noise to the model.
So for implementation and training, our classifier compares MLP and random forest to determine the best accuracy as well as prediction time. As for regression, we use MLP again to train and test our classification results to estimate the distance between different pairs. So for classification, we decided to use MLP due to it having a lower false positive rate, lower prediction time, and higher prediction accuracy for both test and pair accuracy. As for regression, using the classifier results, we trained and tested the same configuration used on the MLP classifier and determined that the hidden layer size of 50/50 produced the lowest mean absolute error in the near perfect R2 score.
Looking at the residual distribution for optimal regression, the MLP 50/50 configuration, you can see the errors are tightly clustered right at 0. With a mean residue of just 0.002, our model proves to be completely unbiased and highly precise in its distance estimation. Moving to prediction time, computational efficiency is just as critical as accuracy. Our 50/50 architecture is exceptionally fast, with an inference latency of only 5.8 milliseconds. It significantly outperforms the deeper, more complex network, making it ideal for real-world application. To wrap up, our hybrid feature fusion frameworks provide a robust solution for indoor localization. We achieve roughly 91% classification accuracy for reliable LOS and NLOS identification. Furthermore, our regression model achieves true centimeter precision, specifying a mean absolute error of 1.77 cm and R-square of 0.998. At under 6 milliseconds per year prediction, this framework is fully capable of supporting real-time positioning updates and mitigating UWP signal bias. Here are the references that guided our research. Thank you for watching.